Chapter 3 In the Digital Domain. Section 1 Analog to Digital Converter. Our signal is about to enter the magical realm of digital information. A lot of the concepts we will see in the coming pages are applicable to video because, in fact, what audio does with sound, video does with images. Capture analog information and convert it into digital information for storage and manipulation. It all starts with the analog to digital converter. If we summarize our signal path so far, we have created sound and captured it with a microphone. That is essentially it. All the stuff in between, mic preamp, outboard compressor, etc., only serves the purposes of enhancing the signal one way or another. How do I record the sound I captured? But we have not recorded anything yet. The signal coming out of the microphone or preamp or outboard compressor, depending on your setup, would simply be lost forever. Sad, is it not? To make this story a bit less sad, we need to record this performance or find a way to write this information somewhere so that we can retrieve it later. Nowadays, this is done on a computer called a Digital Audio Workstation, or DAW, D-A-W, which we will study in Chapter 3, Section 2. Yes, I am ignoring the glory days of tape cutters, serial delays, and manual fader automation. Lots of information about this topic can be found on the interwebs. What is an analog to digital converter? The problem is that computers do not speak electrical signals too well. They speak binary. So we need to find a device to transform an electrical analog signal into a digital binary signal. That is exactly what an analog to digital converter, AD converter, also known as A to D or AD, does. It translates the analog frequency information contained in the electrical signal coming out of the analog domain into digital information which can be stored in the DAW's memory. Once it is stored, we have a choice of playing it around with it, see Chapter 3, Section 3, or replaying the sound, we will see how in Chapter 4, Section 1. Sampling audio. What does sampling mean? When an analog signal enters an AD converter, the converter measures the electrical voltage X times per second, where X is the sampling rate SR, usually expressed in Hertz. A typical sampling rate of 44.1 kHz means that the voltage corresponding to the incoming audio will be measured 44,100 times per second. Each of these measures is called a sample. A sample rate of X Hertz can only accurately reproduce a sound of maximal frequency of X over 2. This is the Nyquist frequency. For example, a 44 kHz sampling rate can only accurately reproduce signals with frequencies lower than 20 kHz. Why not 22 kHz? Because the filtering off has a slope in dB per octave, exactly like an EQ filter, and will take some time to cancel the signal 100%. This is the Nyquist-Shannon theorem, famous in information theory. You need at least 2 sampling points per cycle to accurately reconstruct a sine wave. A sine wave cycle is the time difference between 2 points having the same amplitude. What is hidden behind this seemingly trivial assertion is the fact that we can exactly reproduce an incoming analog signal using a finite amount of digital information. Aliasing, jitter, what are they? If the sampling rate is too low, for example sampling at 16 kHz for a 12 kHz sound, aliasing will occur. When reconstructing the waveform from the sampled points on the way out, the resulting wave would have a lower frequency than the original because sampling with less points than 2 per cycle gives you a signal with a lower frequency. The remedy? An anti-aliasing filter, like an EQ low-pass filter, starting at the Nyquist frequency to cut off any greater frequencies in the signal. How does the converter know that it is sampling at 44,100 times per second? It does because it uses a reference, usually called a clock, go figure, to know how accurately it is sampling. Why is this important? Well, imagine what happens if on the way out, digital to analog conversion or DA, the clock used to reconstruct the signal is not exactly synced with the in-sampling clock. Jitter will occur. Voltage Analog values will be assigned to bit digital values at slightly incorrect moment with respect to its intended time placement. This will distort the sound and add harshness described in many articles about jitter. There is, however, a case to be made that jitter cannot be perceived by most people in a standard non-high-end listening environment. The higher quality of converters in mass consumption electronics might be another reason why complaints about jitter are not any louder than what they are. Section 2. Audio interface. Now that we have converted our signal into discrete, separate bits of binary information, we are ready to start playing with it, right? Right, but where does this conversion physically happen? Where is the AD converter? That is where the audio interface comes in. If you are using outboard AD converters, you should not be reading this book. What is an audio interface? The audio interface is simply a bundle of audio components, most of which we have already discussed. However, because they are so pervasive in home and project studios, and because their accessibility, both in terms of price and required technical expertise, is a large part of what has made audio more widespread, audio interfaces deserve a section of their own. An audio interface can either take the form of an audio PCI type card to insert into your favorite computer, or of a separate hardware unit connected to a computer via USB, FireWire, or some other means. In its simplest form, the audio interface is an AD converter and a DA converter. In higher-end models, it can also contain components such as mic preamps, EQ filters, compressors, MIDI input and output connectors, etc. If we look at Figure 14, we have a single microphone connected to the audio interface, usually via an XLR connection. Within that audio interface, a microphone preamplifier adds gain to the signal so that it can be properly processed by the AD converter. Out of the AD converter go the bits corresponding to the analog signal captured by the microphone and into the output of the audio interface, the DAW, usually via USB or FireWire connection. Once the signal is stored, it can be played back by reconstructing the analog information from the digital information in the DA converter, and then out of the audio interface into the speakers, usually via an XLR or jack connection. I want to buy an audio interface, help me! As you can see in Figure 14, the audio interface is the central device in this example. It acts as the go-between between the analog domain and the digital domain. You will find in the table below some famous audio interfaces for home or project studios. The pros usually use larger units, such as consoles. Table 9 shows famous audio interfaces. It has 9 columns: vendor, model, price, connectivity, A to D converter type, phantom power, MIDI, inputs, and outputs. Vendors represented are Apogee, Avid, Focusrite, Lexicon, M-Audio, Mackie, Modu, PreSonus, Roland, and Steinberg, with prices ranging from $50 to $600. For each microphone, XLR or combo, input connector, there is a corresponding microphone preamp in the unit. The quality of the preamps is one of the factors influencing the price of the unit, but not the only one. Other factors include, in no order, the number of connectors, the quality of the AD and DA converters, the presence of digital meters, and the inclusion of a MIDI input and/or output connector. Section 3. Digital Audio Workstation. What is a digital audio workstation? The Digital Audio Workstation, DAW or DAW, is the brain of the audio system. It stores the digitized sound. It feeds information to software plugins for digital processing. It then feeds bit music to the DA converter to transform the processed digital information back into analog voltages. The DAW, from a technical point of view, is a computer, hardware, and operating system with specialized processing software installed on it. The audio interface drivers are technically part of the operating system. You could say that the audio interface extends onto the DAW, but that would not make things any clearer, would it? When they speak about a DAW, most people mean the processing software itself rather than the whole system, most likely because hardware is so ubiquitous these days. Before you ask, both PCs and Macs are worthy choices for DAW hardware. I want to buy a DAW, help me! In the table below, the most popular DAWs are presented. I'm not going into the which one is better debate because frankly, it is pointless. Do I argue about what socks you should be wearing? The table has 5 columns: vendor, name, version, price, and main selling points. Prices range from free to $1,800. How do I work with a DAW? Working with modern DAWs is usually very easy. You start by recording tracks directly from the audio interface or by importing tracks, usually in uncompressed WAV format, WAV, into the software. Arranging the tracks in some logical manner should be the next step. Modern productions can contain over 100 tracks, the norm being around 50 to 70 tracks. Labeling, giving tracks a color, grouping tracks by instrument type, these methods help make sense of the structure of the recording. Routing information from one track to another or from one track group or bus to another helps minimize the logical signal path. Once that is done, the tracks can be mixed. A balance must be found between these instruments and voices. Some elements need to be refocused or corrected with the list of effects described in Chapter 2, Section 6. Gates, reverbs, compressors, EQ, etc. Anything works if it sounds good. These effects are usually associated to a track in the form of a software plugin in one of many formats, the most well-known being VST for Virtual Studio Technology developed by Steinberg, and AAX, Avid Audio Extension, developed by Avid. Once the balance is found and all the elements in the mix have been properly taken advantage of, a portable version of the mix is exported to an audio file so that it can be distributed and consumed. Storing audio. What is the bit depth? The data captured from the sampling described in Chapter 3, Section 1 is digitally stored in numbers represented by bits. The total number of bits available to store the information contained in each sample is the bit depth BD. The larger the bit depth, the more amplitudes of that sample can be recorded and stored. Note that the bit depth does not impact the accuracy of the signal sampling. That is the job of the sampling rate. What is the dynamic range? What the bit depth has an influence on is the maximum loudness of a signal, represented by the dynamic range DR max or signal-to-noise ratio SNR of the signal. DR max is 6 times the bit depth. For a 16-bit system, BD equals 16, DR max is approximately 96 dB. For a 24-bit system, DR max is 144 dB. The dynamic range represents the height of the sampling window. Whatever is larger cannot be sampled accurately. The raging debate about which bit depth should be used, 16 versus 24 bits, can be put to rest with simple comparison tests. Listen to a song at 16 bits and then at 24 bits. I can guarantee you that most people will not hear the difference. But everyone still uses a 24-bit depth, including me. You never know. What does 0 dBFS mean? One note of importance. Most DAWs will show you sound volume in dBFS for full scale with a negative value. Why? Because 0 dBFS is defined as the maximum capacity, the bit depth, of the AD converter. Thus, any sound will have a negative value lower than 0, which is the maximum. What happens when you work at 24 bits but then decide to export your file at 16 bits? We are losing information, are we not? And that is bad because losing information means losing the possibility to reconstruct the original sound without artifacts and distortions, right? Yes, but there's a way around the problem. A technique called dithering uses the fact that our ears are very good at picking out individual frequencies from a sound, but bad at picking out random noise at many frequencies. Dithering mixes in random noise into the original sound to fake our ears into thinking every bit of information is there. This process is also used when moving up the bit depth ladder instead of down. Audio bandwidth. What is audio bandwidth? Audio bandwidth is the amount of audio data passing through some device. It is expressed in kbps for kilobit per second, or 1024 bits per second, and is called the bit rate BR. It is the bit depth times the sampling rate times ms, where ms is a mono stereo variable. Mono, ms is 1, and stereo, ms is 2. Standard CD sound is usually stereo, ms equals 2, and transmitted in packets of 16 bits, BD equals 16, at 44.1 kHz, SR is 44,100, giving a bitrate BR of 1,411.2 kbps. At that standard rate, a 3-minute or 180 seconds song would be large at 260 megabits or 32.5 megabytes. 1 byte is 8 bits. What does MP3 mean? At the time when digital audio started to become popular with the use of CDs, network bandwidth and disk sizes were not large enough for files that size to be practical. Thus, audio files were compressed. Compression is the process by which the amount of information used to represent or encode a file is decreased. Lossy compression is the same process but with loss of information. For example, the popular MP3 format is the result of lossy compression. MP3 means MPEG-1 or MPEG-2 audio layer 3. The technique used is based upon an effect called masking. A weaker sound is masked by a louder sound at similar frequencies. This means that instead of representing the information of both sounds in the file, only the information of the louder sound is encoded into the file. Standard MP3 usually has a bitrate of 128 kbps. That is 10 times less than what our calculation above has come up with. But with that bitrate, the song size is also divided by 10, which gives the standard 3 megabyte per song. With a standard 16-bit audio system, that is a sampling rate of 4 kHz in stereo. Compare with this CD standard sampling rate of 44.1 kHz, and you will understand why certain people consider MP3 style compression an aberration. Is it good enough for you? Only your ears can decide. Note that MP3 encoders can vary depending on the algorithm used. Also, MP3 file formats allow bitrates up to 320 kbps to be used. With bigger bandwidth and larger storage capacities available, audiophiles prefer to listen to music encoded in lossless compression formats such as FLAC, FLAC for Free Lossless Audio Codec, which can reduce the size of an audio file by 50 to 60% without altering its quality. Latency. What is latency? We know that a converter creates samples by measuring the incoming electrical voltage. As it works through the signal, the converter places the samples in a temporary memory location called a buffer. When the buffer is full, the computer retrieves all the stored data in one operation to process it. The reason for this mechanism is that the computer might be busy doing other things as it is processing the signal. If it is too busy, it might miss certain samples, introducing distortion artifacts in the rendered sound. Imagine a factory worker putting pieces in a box. If the conveyor belt moves too fast, the worker will miss certain pieces. The latency L can be calculated as the buffer size BS, the number of samples, divided by the sample rate SR. Therefore, you will hear audio engineers say, "Man, this buffer size is total BS." Why do I care about latency? For example, a fast computer might accommodate a buffer size of 64 samples for a sampling rate of 44.1 kHz, since the latency produced will be about 1.5 milliseconds. A slower computer might need 512 samples to avoid distortion, but this would generate a latency of about 11 milliseconds, which can be an issue if you are recording drums with a click track, for example. You can increase the sampling rate, thus reducing the latency. For example, a 512 buffer size with a sampling rate of 96 kHz produces a latency of about 5 milliseconds. In turn, increasing the sampling rate might force the computer into missing some samples, thereby introducing the infamous distortion. ASIO, audio stream input-output drivers, allow you to change the buffer size on the fly. This change can be expressed in latency terms. For example, you could set your buffer size to high latency for slower computers. Do you know which company invented ASIO drivers? Steinberg. Again? Yes, Steinberg was a huge player in the early developments of audio technology. The time it takes for a computer to sample the incoming sound is in direct relation with its computing capacity, its processing speed. With a slow computer, the buffer size must be larger. If you try to reduce the buffer size, crackling noises will appear. The best way to strike a balance is to experiment with various settings, buy a faster computer, or outsource the computing to outboard gear. Section 4. MIDI. What is MIDI? We take a small detour from our signal path. So far, the sound has been produced and recorded in a DAW. It might have been processed, changed, altered, or modified. Or not. But what if you want to add another instrument? Say that you wanted to add a flute to a song you are working on, but you cannot play that instrument. Composing music is one thing, and playing that composition with all the planned instruments is another. A musical instrument digital interface, or MIDI, might prove useful in this case. It will allow you to create sounds representing any instrument from a MIDI instrument called a controller. You need three things to make it work: someone performing with the controller, a way to communicate between the controller and the computer, and a sound representing the desired instrument stored on the computer. The first item is taken care of very easily. You can buy MIDI controllers for dirt cheap or even ask your smartphone to do it for you. The most common type of controller is the keyboard type controller. There are also wind type MIDI controllers, allowing for a very rich range of note expressions. Percussion controllers allow you to play drums on a real instrument and modify the drum's sound later. The second item is where MIDI comes in. MIDI is a messaging standard which communicates note information digitally. Amongst others, MIDI messages contain the following items: note number, note velocity, note on timing, note off timing, volume, pitch bend, and channel, 16 channels maximum. Notes range from C1, around 8 Hz, to G9, 12.5 kHz. This information can be encapsulated in a file with the SMF, for standard MIDI file format. Where is the instrument information? It is not included in MIDI. MIDI only contains note information, not instrument information. A lot of people associate MIDI with 80s video game music sounds. That is only because computers have a very basic set of sounds in their sound library, so when played with a default PC setting, MIDI sounds awful. How do I use MIDI? However, and that is where the third item comes in, sound libraries, also called sample libraries, nowadays contain hundreds of thousands of sounds, from percussion to strings to guitar to voices to winds to special effects. If it can be recorded, it can be sampled. The process of creating these samples is extremely time-consuming. You record each sound multiple times in various conditions so that when it is played by the computer, it sounds like a real instrument. In the more expensive sample libraries, you can find the same instruments played in different manners, like, for example, a violin played pizzicato or a guitar played muted. The only thing you need is a piece of software to play these samples per the MIDI information contained in the MIDI data transmitted from the controller. Yet another use for your DAW. This is how you would create that flute track in your song. First, get a MIDI controller and hook it into your audio interface. That is why some of them have a MIDI in connector. Second, open your DAW of choice, add a track and prepare it for recording. Third, perform the flute part on the MIDI controller while recording it on the computer through the DAW. What happens if you now press the play button in your DAW? Nothing. Why? You have not told the DAW with what instrument it is to play those recorded MIDI notes. Add a sample playing plugin to the track, select the instrument, et voila, you now have a flute leading the way in your Swedish death punk song. The power of MIDI resides in the fact that it is very flexible. You can use it with any DAW, with any MIDI controller, with any sample library. You could also buy a computer or smartphone application to generate MIDI notes and music scores for you. If the format described above is respected, you're good to go. Because sample libraries are recorded so well, it is becoming increasingly difficult to tell a sample from a real thing. There are exceptions, of course. Stringed and wind instruments come to mind, but for most intents and purposes, a single sample will do just fine.